Yes. Hello. Hi. Hi. Hi.
So we are moving down the day now and trying to find a little bit more concrete approaches and embodiments of self-organizing networking algorithms. And I'm very happy that Maria agreed to give a talk today. She's right now finishing a PhD on SON, on machine learning SON, and so she's probably the best person to talk about these type of issues. You know, I've given building blocks. She's now giving the algorithms in the building blocks. She's done the MSc in UPC.
Yes.
Yes. And now she's with us at CTDC. Well, the floor is all yours.
Thank you. Thank you, Misha, for the introduction. So let's start. Okay, as Misha said before, what I do is to apply learning techniques in order to get some self-organization capabilities in the specifically in Femtocell systems. So the idea of this talk is to show you how to implement online learning algorithms. So the outline of the presentation will be as follows. First, I will give a very brief introduction of self-organization and more specifically self-organization in future networks. Then we will go for the machine learning, which is the technique which allowed us to implement the self-organization techniques. And more specifically, we will go to reinforcement learning algorithms. Then we will stop here and I will present you the problem we aim to solve and the simulation scenario we use to validate the proposed solution. And then we will continue with more specific matters about the design of the decentralized learning algorithms. Then we will see some simulation results and some of the implementation limits of this learning system. And if we have time, we will go for the proposed solutions we have for these problems. One of them is based on a cooperative technique which we call Docitive, and the other one is based on the combination of fuzzy logic with the Q-learning algorithm. And the main idea with this combination is to have more accurate representation of the environment and the actions we can take. So let's move. Okay, we all know what femtocells are, so I will not talk about it, but the idea with this slide is to introduce the necessity of including self-organization techniques in femtocell systems. As you all know, femtocells are located by their end consumers, and therefore the amount and location of them are unknown for the operators. Which will make it impossible to introduce centralized planning and control from the operators. Another aspect to take into account is that femtocells are a very important component of the heterogeneous networks, the future networks, so they have to implement some energy efficiency techniques, they have to be autonomous, intelligent, etc. So the idea is to take advantage of the introduction of the concept of self-organization in next generation networks, and self-organization concepts is the ability of a system to spontaneously react or tune its components or parameters with a purpose on following certain conditions of the system or thresholds, as you can if you want to say it, and without the help of any external agency. So this will be decentralized. From our point of view, there are three main techniques or groups of self-organization. We divide it in self-configuration, self-optimization, and self-healing. The first group, self-configuration, will comprises all the algorithms for the setup configuration. So this means that when a new entity starts or arrives to the system, it it will use this kind of cell configuration systems to initialize its process. So a good example for femtocells for self-configuration algorithms will be how femtocells can get its IP address. Then we have the self-optimization algorithms. They comprises all the algorithms which allow to the entities in the system to tune or to arrange some of the operational algorithms or parameters as a response to the change in the environment. So these techniques can be applied for radio resource management, for example. And finally, we have the self-healing algorithms, and these algorithms will allow the entities in the system to give solutions in case of failure. These algorithms can be implemented in a single entity or can be also cooperative. When we talk about cooperative self-healing algorithms, can be seen as two main groups. In one of the groups, we can have solutions. They look for solution in a cooperative way, or the other way to see it is that the other component of the system, but the one with failure or with problems, will try to cover or to minimize the damage that this node is bringing to the network. So we focus in this talk, we will focus in a self-optimization algorithm. And okay, the main characteristic of self-organization system is that they are decentralized, and the organization or coherent behaviors are achieved due to interactions between the elements in the system. And a very interesting characteristic of this kind of system is that they achieve the organization in a parallel and distributed way. This brings important gains in terms of reduction of the operational expenditure due to the autonomy that the agents can achieve. Also, the improvement of the adaptability and coexistence capabilities, and this is because the agents or the entities in the system will be able to react to change in the environment, and also an optimization resource utilization, because each entity in the system will be applying an optimization process, and this will translate in a global optimization process. So in future wireless networks, we will require the introduction of significant degree of self-organization capabilities due to the large number of tunable parameters and their interdependencies, and also because we will require multiple cells in order to give the required coverage and the capacity that new applications require. And here self-organization will bring important solutions, or can give good solutions in terms of the coexistence and coordination between these multiple cells. So some examples of applications of self-organization for wireless system can be found in radio resource management, for example, for handover control, for admission control. Also, we can find it for power management, for the configuration of some antenna parameters, also to find the an automatic neighbor relation, and so on and so forth. So, okay, now we have the concept of self-organization, and now we will see what does it mean in reality. So self-organization is based on the sensing and optimization process. What we mean with sensing is that it can be based on the example data if they use sensor systems, or they can be based on past experience when we use databases. So the logical way that we found to apply self-organization was through learning algorithms, because they allow us to translate example data into actions. And here is where machine learning arises. Machine learning is the branch of artificial intelligence science where it's in charge of the study of algorithms, of the study and the design of algorithms, which allow to evolve behaviors based on the example data. Okay, so we will have two types of learning algorithms. They can be centralized or decentralized. Centralized systems have a very good performance because they will have a global picture of the state of the environment, but it presents significant implementation issues in terms of security, since it will have a single point of failure, and also in terms of scalability. We can solve very short problems with this kind of learning systems. Also, we will require signaling interchange between the to have the view of the environment, and also, of course, this will introduce some delays. So the centralized system will solve all these issues of the centralized system, and besides, it will allow an online optimization, which is very good because it will be able to learn online. But the problem is that this type of learning are still a hot topic in the artificial intelligence and machine learning communities because there is no a proof of optimal solution. And they also present some problems in terms of convergence due to the interactions between the multiple entities learning simultaneously. In any case, I can tell you that it works and it's very interesting, so we go in this decentralized learning algorithms direction. So taking the concept of Tom Mitchell, which is one of the precursors of machine learning algorithms, we can say that a computer program learns from a given experience in a given task when it is measured by some performance. When this performance for the given task improves with the experience. So there are different types of machine learning algorithms. We have the supervised learnings. This type of learning is mainly used for classification process. It is based on functions which will classify given inputs into desired outputs. And these kind of algorithms require a high human intervention. So in order to design the function, to see what we want to have at the output, etc. So then we have the unsupervised learning, and these algorithms are used mainly for find structures on level data. So it's very used, for example, for imaging processing, etc. This kind of system where you have to find some relation between data. And finally, we have reinforcement learning. Reinforcement learning is based on the the learning process is executed based on the interactions with the environment, and that is why it's called reinforcement, because it will be based on trial and error. The agent will try and try and try and see how the environment is responding to the actions. So yes.
How do you exactly differentiate supervised learning from reinforced learning?
Pardon me?
How do you exactly differentiate? Means what's the key difference between supervised learning and reinforced learning?
Because in supervised learning, and as I said before, you will need the intervention of someone designing the function. In order to classify, you will have a group of inputs values, okay, and you know what you want to obtain at the end. So you know as designer what are the outputs you want to have. Yes, okay. And you have to design a function which will classify those inputs into outputs. Okay. So it requires that somebody, a person, is there designing all this, and also being sure that the outputs are what you are expecting.
Okay.
Because it's for classification mainly.
Yeah, because I always find it difficult to differentiate, because in reinforced learning the environment acts as a supervisor, because if you are facing a penalty so somehow you know that it was wrong.
Yes.
So it means somebody told you it was wrong.
Yes, but well, we will see more in details reinforcement learning, but the good thing of the reinforcement learning is that after you characterize the state of the environment and the actions you can take or whatever, and how you will measure with the reward function, you don't have to take care about it because it works. Okay. So you don't need to be there seeing if it's working.
Okay.
Do you know what I mean? We will see it in more details, but from my point of view, reinforcement learning is good because
compared to supervised,
you don't need you don't need an environment model, and you can have online learning, and this is the main characteristic for reinforcement learning. If you design it well, you will be able to learn online. So it's like real learning, real life learning, let's say.
Thank you. Okay. Thank you.
So the main idea of reinforcement learning is that the agent will try to take actions in the environment in such a way that they will minimize the notion of the costs in the future, or will maximize the reward, depending on how you model your reinforcement learning. You can maximize a reward in the function or minimize a cost function in the future. We will model our reinforcement learning as minimization of the cost function. So you will see always C and minimization. Okay? So reinforcement learning for single agents are modeled based on Markov decision processes. They are formed by a set of states describing the environment, a set of actions describing the actions you can take in each state, a cost function which will map the states into actions, and you will have a real value giving you the how good or how bad is the action you took. And finally, it's characterized by a state transition function P, which is the probability to transit to one state to another after the execution of one action. So this is for, as I say, this is for single agents. As we want to model decentralized learning algorithms, we need to add another component, which is the set of agents in the system. And when we model this as multi-agent systems, we have to see this problem as an stochastic game, where when each agent will take actions, it will approximate the other agents in the system as part of the environment. We introduce, as you can imagine, we introduce the concept of multi-agent system because it will allow us to solve more complex, large, and unpredictable problems, which is our case. We have a very complex system, a lot of femtocells, and it's a wireless network, so it's very difficult to model it. So we think that if we are able to decentralize the learning processes, we will have very interesting gains. So please don't get scared with these equations. I just want to show in what consists the reinforcement learning. So the majority of these algorithms are based on the computation of the state value B and the action value Q. The idea with these equations is that the agents will try to find or to maximize or minimize, in our case, the notion of the cost function during the time. Okay, so the idea is that they will try to evolve or to find optimal policies, which will translate into which will be actions. Policies will be the actions you have to take to find optimal behaviors for both cases, in case of the state function and the Q function. And well, just to show you how it works is you will have an state. For the case of the state value, you will have an state. And the optimal policy will be that action which will give you the low cost. And for the case of the Q function, it will be the action that will give you the cost, the minimum. Well, you select the action and you will have the minimum cost following the policy thereafter. We see it here. Okay, so the idea I want you to keep is that you can have state values or action values. The state value will measure how good is to be for an agent in a state, and the action value will measure how good is for an agent to execute an action in a given state. So this is the main difference. Okay, I want you to keep this one in mind. The Q function is how good is for an agent to execute an action in a given state. So as we saw, we need to know the probability distribution. So we need to know what probability we have to go from one state to another. When this information is available for the agent, the reinforcement learning process are solved by dynamic programming. Since this will not be our case because we cannot model how the environment will behave, this is quite complex for wireless systems. So we have two options: the Monte Carlo methods, which are based on the construction of maps of states, actions, and rewards. So you need to build somehow how it behaved in the past. Or we have the temporal difference methods, where the knowledge will be acquired due to interactions with the environment. So we focus in this one because we want the online learning. We want just agents to learn interacting with the environment. So among the different temporal difference algorithms, we have two main groups: the actor-critic methods and the Q-learning and SARSA methods. The difference between these two groups of methods is that the policy will be obtained. So for actor-critic methods, we will obtain modifiable policies which will tell us the tendency to select an action. And on the other hand, we have the Q-learning and SARSA algorithms which at the end of the learning process will tell us which will be the best and the worst action to take for a given state. So we go for these ones because after a learning period, we want the agent to know which is the best action to take in just one shot. Okay? So now we go for the... We will see the difference between SARSA and Q-learning. Actually, these learning algorithms are quite similar. Both of them are based on the computation of the action value, the Q value that I showed you before. And the main difference is that SARSA is an on-policy method. This means that in the update of the Q value, it will consider the policy it is currently following. We will see this in the question afterwards. And a good thing to remember this algorithm in the name is that the name is given by the current state, the current action, the current reward, the next state, and the next action following the policy. That is why it has this name. And then we have the Q-learning algorithm, which is the contrary, is an off-policy method. And this means that the update of the action value will be based on the best action for the next state. We will see this in the question again. But the idea is that once it finds a good policy, it will follow it. This will give us, well, we will see this in the example better. So we take a very common example for reinforcement learning systems, which is in the Sutton and Barton book called Reinforcement Learning, an Introduction. If you want to go more into detail, I really recommend you to find this book. It's in the web, so it's very easy to find. And the idea is this one. We will have a starting point and a goal point, and the agents have to learn how to walk next to a cliff. So we will have the optimal path where the reward will be good, and then we will have the safe path, which is far from the cliff, but it has a cost. if the agent falls in the cliff, it will have a high penalty. So the Q-learning will follow the risky policy, let's say. Once it finds the optimal path, it will follow always this path, even if due to the greedy action selection policy that we will see afterwards, it will fall sometimes. So that it will have worse rewards, but better behavior if you look it in the average, no? And on the other hand, SARSA will follow always the safer path. So it means that you will have less risk, but longer learning periods. Okay, so now we stop here and we will go to the problem. We will see the problem we want to solve with the proposed solution, and we will see the simulation scenario. So if you have questions, this is a good moment. No? Okay. So we go back to the first slide, and the idea here is that since we know that the femtocells are randomly deployed, and we will have probably a lot of femtocells, just because a lot of people said that we can consider femtocells as isolated systems due to the wall penetration, the low power transmission, but if we have dense deployed scenarios, the aggregated interference that they may generate in the potentially closed macro users can be high. And this is what we try to solve. So we focus in find a solution for a decentralized interference management problem when we have aggregated interference coming from the femtocell system in the downlink direction. So we introduce the self-organization capabilities here in order to favor the scalability of the network, the femtocell network. Also, in order to be able to support dynamics inherent to these femtocell systems, and also because we think that with these techniques we can highly reduce the signal overhead. So this is the problem we aim to solve. What we want to do is that each femto base station in the system be able to learn a policy to allocate power for each resource block in such a way that it will not interfere the macrocell system. So we will have per each femto base station a learning algorithm per resource block to learn which policy to assign in order to don't interfere with the macro user using that resource block. So our objective is that interference at the macro user can be kept at a desired level independently of the femtocell density in the system and the activity pattern they have. So we continue. This is the scenario we use to validate the solution. We follow a 3GPP technical report where they, well, we have seen this in several presentations. Yesterday, actually, Subin used it. It's based for interference modeling in a femtocell system. We use a dense deployed scenario. First, we deploy 19 macro base stations with each one with 3 sectors. And we assume that macro users are randomly deployed and are always outside. And then the femto base stations were deployed following the dual strip model, where this represents a building with 2 blocks of apartments, and it has a probability distribution to have, which determines if inside an apartment there is a femtocell or not. We also assume that femto users are always indoor. And finally, we go back to this slide in order to show you the path loss models we use to characterize the channel, and well, those are in the technical report, 3GPP technical report. We also include fading and yes. Okay, so now we can continue with the learning process. Now we go to the core of this presentation. We will see how to really design a learning algorithm. So the main idea in the online learning is that each agent or the agent will sense the state of the environment. So it will represent how the environment is in that moment. Based on this information, the agent selects an action following an action selection policy. We will see this. Then, as a result of the execution of the selected action, the environment will suffer or will make a transition to a new state, which we call B. And this transition will generate a cost for the agent, okay, which evaluates the consequence to execute the action in the given state. And this cost is feedback to the agent, and the process is repeated. Okay? So what's the state? In the state, when we want to define the state of the environment, we have to include the relevant information and compact, so it has to be important information regarding the environment we want to model. Okay, so if we want to control interference, we need to model somehow or to have some information about it. If we want to control power, the same. So we need to include important information in here. The actions are the parameter we want to learn, and the goal or the idea is to find the optimal action to be executed in each state. Then the cost function is one of the most important characteristics in reinforcement learning algorithms, because it has to tell the agent what is its goal. So we have to correctly relate the state characterization and the actions the agent can take with this cost. And finally, we will have the next state, which is the resulting environment state after the execution of the action. So now we go into details how we model our system. First of all, to recall that we will implement a learning task per resource block in each femtocell, and then we have this the state of the environment represented as follows. We will have a component for the total transmission power of the femtocell. This will be all the power it transmits in all the resource block. Then we will have a component for the capacity of the macro user for the given resource block. Then, and finally, we will have the capacity of the femto user for the given resource block. And the actions will be the different power levels that the base station can assign in each resource block. And the cost function is as follows. We will have a high cost value if the total transmission power is above the threshold, which we set up at 10 dBm following the Femto project requirements. And also it will have a high cost value if the capacity at the macro user is below the threshold. In this case, we set this value at 1.4, if I don't remember bad, yes, 1.4. So finally, if these two constraints are fulfilled, the agent will try to maximize the capacity of the femto user. Yes, of course.
Slide seems like the core to the whole reinforcement, the multi-agent learning process, let's say. So the big question to me is, who determines the states and how?
Okay.
And who determines the cost function and how and why?
So since the reinforcement learning is designed by someone, the designer has to define the state of the environment and the cost function. Of course, when we were designing this, we tried a lot of things, and this was the best balance we find. You can have very, very simplistic cost functions like 1 or 0, and that's all. You can have very simplistic scenario representation, just one component, or you can have also very complex ones. So this depends on the designer of the learning algorithm.
Yeah, I understand. Yeah, but you know nothing about how far you are from optimality.
No.
You have no idea.
No.
And is there any work in place which tells us how good we are? I mean, you have chosen here a negative exponential cost function with respect to capacity. Why? You know, I mean, you look at this and you wonder, why did you choose it? It's always this was my core problem with all reinforcement learning literature, with all of that, with no exception. You know, it's playing around. You're cooking, you know, but you're not designing in a sense.
Yes, exactly. Well, it's true, because at the end, with reinforcement learning, you have to try. It depends a lot of the problem you aim to solve. So you have plenty of opportunities, and that's true. You don't know how far you are from optimality. And more if you are applying this for multi-agent systems, as I said before. So there are some works going on. I start working on some things regarding this, but it's very complex to find the optimality when you take into account the multi-agent systems. Okay, so yes, for reinforcement learning, the beauty of this system is that you can do whatever you want, or just since you can have or design well these two or the three components. So this is the good thing, and the bad thing is that is the other one you just mentioned. You don't know how far you are from optimality. Of course, this depends on the imagination you put in the design, and also in the the problem you aim to solve.
Well, I like reinforcement learning because I think this is how we humans function. Exactly. You know, it's an input, you process it, you give some weights to certain inputs with respect to outputs. Okay, so if you walk over a red traffic light, it's bad news. You learn it after a while, so that's your negative reward. Okay, we operate like this, but I think the human brain doesn't have this slide. This slide is blank when we are born. Okay, exactly. So taking this a little bit further, why don't we just start with a completely blank sheet and start actually also learning the states and the cost function? Because you are the overall goal of humans is to survive. It's a single goal. Okay, so the overall goal of your system is to have maximum capacity. You know, let the rest just evolve over time. Do you think this is possible?
This is a very good question. I think we could go, but the thing is that you need to know what do you want to do.
Well, I want to maximize capacity, full stop.
Exactly.
I don't even know about all this, okay?
Okay,
I don't know about thresholds. I don't know anything about power states. You know, I know a few parameters I can tweak, but I don't know the granularity. I don't know the maximum values, minimum values, etc.
So the way to proceed, from my point of view, is trial and error. You don't know which will be the best state to represent your environment. You just know what you want to do. So you just start trying different possibilities for the states, and the same for the cost function. So
it should work.
Pardon me?
Do you think it will work?
Yes, of course. You can actually. I'm presenting here just one of the best solutions I have found. But
you have tried the best solution. You have tried, yes, yeah.
I have tried different state representations and cost functions, and yes, this is a good solution from my point of view. But that is the idea of this talk, to encourage you, to all of you, to try maybe these techniques, and we can find better solutions, of course. And we can not only control the capacity. Other problem of this kind of system, which is very interesting too, is that if we could manage not only one parameter but several, this could be great. But once you incorporate in the cost function different parameters you want to optimize, the system becomes crazy sometimes. So this is very interesting, because if we can combine parallel learning algorithms or maybe make much more complex learning algorithms, it will be great. But the idea here, or the problem here, is how to do this. And this is an open issue, and if you want to work about it, let me know.
So what you mean is that instead of taking exact forms of this cost and state functions, you should keep them as general functionals. You know at least something about, say, cost function, that if your, say, power of Femtocell is greater than the max power you want to, so your cost should actually be kind of increasing function. At least that much you can, to some extent, assume. And then otherwise it should be some decreasing function, maybe a monotone function. So why not to formulate this problem in terms of maybe a functional space and then look at it? Is that what you mean? Paraphrasing you?
Yes. It's, I think, very complex. I'm not sure Paul is there.
Yeah, it's going to be hard. No, but there is some structure to the problem, right? At least you know what you want to do there. So
yeah, I think what could be possible is that you just you don't learn actually closed representation of the cost function. Okay, you don't know whether it's exponential minus something, but you just get an empirical realization of the cost function. I think that is something I could imagine could be learned, and maybe that's the right way to start. Maybe the state space is something we can have as an input, but I think the cost function is one of the biggest weaknesses, in my opinion, in terms of optimality of the reinforcement learning. I think that is something maybe which could be learned.
Yes.
I'm not saying there's we have been talking about this a lot, but yeah, I think that's one of the problems why it is not entering the industrial space, because what happens is we observe there are many cases where it is not stable.
Yes. Exactly.
You just cannot guarantee that it will work. So you need to tune and tweak a lot of parameters until it works. And I think that is a real weakness. You want to make sure that if this parameter space doesn't hold anymore, it automatically relearns it.
Yeah, but I don't know if this. I'm not sure we can try, but I'm not sure it will work, because if this is not constant, it will introduce high dynamism in the system too, because the agent will lose the objective, or the objective will change in time, and the information you have from the past will not be useful for the future. So I'm not very sure if it
well, I mean, it works with the human. I mean, our cost functions change over the day. I mean, when you talk to me, you have a different cost function when you talk to the boss, so it's very simple.
That's true.
Adding to your comment, Misham, is human beings actually, if you look from psychological point of view, human beings never have a blank slate from the birth. There are two things in psychology. They call it N-square theory, means nature plus nurture. It's not actually plus, it's actually product. Nature is multiplied by the nurture. So if any of them is blank, then the output is 0. So, but the thing and the thing is, here when we are trying to mimic the human mind, we are unable to model the nature which is inherited, or which is because of the genetics there. And we always start from the point, okay, nurture, learning means teach or learn from the environment. So that's why we are lagging behind the actual human behavior, adaptive, which is 2-layer. And to make it 2-layer, yes, as you said, that means we have to look into dynamic functional space, which is quite difficult. So means we are missing in the actual modeling problem.
It's a modeling. It's a problem of formulating the problem, yes, which is the actual problem during the PhD as well.
So I wanted to comment on this discussion. Maybe there is a difference between classical, let's say, decision-making procedures, let's say co-admission control, scheduling, cross-layer optimization techniques, and this one. Maybe in learning, the number one criterion to see stuff about optimality is your decision to be reliable, your decision, the safe path you outlined in your presentation. So I think that maybe a suboptimal decision in learning may be substantially be the optimal for specific situations and context.
Yes.
And maybe in your PhD, you can see, you have seen that.
Yes.
Maybe the optimality is not the number one. You can see specific scenarios and situations that learning
Exactly.
can enhance the whole procedure as a module in the whole. I see it on, I work on context-aware mobile and wireless networking, and I see that prediction and learning modules can assist the whole procedure of decision-making, but it has to be seen as a, from overall perspective.
Tool.
Yeah, a tool.
Facilitate that.
Yeah.
Exactly. So
Because
this is
it has
very.
to do with psychological and the other human.
So
Okay,
yes, this
he's
very
Greek, he's very philosophical, as you see, sir. Sorry,
No,
let's...
actually, this is a very interesting point of view, because the idea with the learning is that maybe we cannot have the optimal solution, because we mathematicians and engineers are very often obsessed with the optimality. But maybe what we need to find is good performance and just to guarantee coexistence, and that's all. We have a system well performing, behaving well, respecting the others, and that's good enough sometimes, no?
Very good answer, because she's at the end of the PhD and going to go to Orange to work, so it's fantastic.
So, did you want to ask something or no? Okay. Okay, so let's move. Let's continue. We still have a lot of things to tell. So as I told you, to remember, SARSA and Q-learning are based on the action value learning, and this learning or this knowledge has to be stored in somehow. So the more intuitive and common way to represent the knowledge is based on the lookup table representation mechanism, where we will have a Q value per state and action pair. So here, no, the people in the streaming don't see this. So here we have the states, and here we will have the actions that the agent can take per each state. So the idea is to learn an action value per each state action pair, and in such a way that if the agent decides or realize that it is in the second state, for example, S2, it is able to know which is the best action comparing the stored Q values for that row. Okay, so the way to proceed to implement a learning algorithm is as follows. First of all, you have to initialize this Q table to a given value, and then you need to observe the current state of the environment. Afterwards, based on this information, as I said before, let's say that we are in S2, we need to select the action following an action selection policy and execute it. We receive the cost, we observe the new state of the environment, and with this information we can update the Q value. Specifically for the Q learning algorithm, this is how we do it. So we will have the old value, and we will update it based on the cost function of the cost value we receive, and the optimal Q value, the Q value for the optimal action in the next state. So we know we are here, we determine the next state, and we choose or select the action, the best action for the next state. And this is the difference, that is why this is an off-policy method, because here in the update it doesn't take into account the policy it's following. And this is the main difference with the SARSA algorithm. As we can see here, for the update of the Q value, it will choose the action following the current policy, action selection policy. Okay, so, yes?
Sorry, maybe it's probably my problem. I don't understand. This matrix is something that is deterministic, or is something that changes along time? I mean, because you say that you update the table entry. I mean, you update the values of Q.
Yes.
But once you have all the actions and all the states, the values of Q are fixed, no?
Yes. Once the learning process finishes, you know how to behave per each state. So this will be fixed.
No, but if you have the number of states fixed, the number of actions fixed, and the cost function fixed, then you have everything fixed in the system. What is changing?
The state of the environment. Because if you are only one agent in the system, if I'm alone here and I don't change anything, so I will be in the same state, executing the same action always, you know, the optimal action for that state after the learning period ends. But we have to take into account that we are all of us taking actions at the same time, and one is starting, other is.
So what changes is the interaction between the agents.
Yes.
So if you only have one agent, meaning one femtocell, then there is no learning process, right?
It will be a learning process at the beginning, because every time you take an action in the environment, you will change the state of the environment. But after a while that you learn the optimal behavior, you will have a stable state. You know what I mean? Because you will find the optimal solution for that state, which will be static.
Yeah.
Okay? But since there is another question, but after a learning period, this Q table is completely updated. The idea is that I will know which is the best action in each state. So if something changes in the environment, my state will change, but I will only need one selection procedure to adapt to the environment. See?
Yeah. Okay.
And in the case of multiple players, will we reach also stable state or not?
We will see it in the simulations, but yes. After some period of learning, they will be able to represent. Okay, this is how you have to model the state of the environment, let's say. You have to take into account that in our case, we will have a global indicator, which will be the capacity of the macrocell. So if this capacity of the macrocell is below the threshold, even though if I'm performing well, because I'm transmitting to good power levels, but the others are jeopardizing the performance of the macro user, my solution will be to transmit at a lower power. And that will be the behavior of all the agents in the system, so at the end they will find solutions for these situations. Yes. Okay. So let's compare both learning algorithms. Based on the definition or the explanation we gave of the difference between both of them, we can see that for the case of here we represent the probability to be out of the thresholds for both the total transmission power and the macrocell capacity as a function of the learning iterations. As we can see in blue, the Q learning is able to decrease this probability much more faster than the SARSA, and that is because once it finds a good solution for a critical state, let's say, it will follow that action always. So this guarantee that it will decrease that probability much more faster than the SARSA. Meanwhile, SARSA will have a more careful learning process, let's say, so it will be slower, but in the long term it will be a little bit better. Okay? And on the other hand, if we analyze the performance of both systems, we can see the same problem. Q-learning is much more risky, let's say, so it will guarantee the capacity of the macrocell, but it will not hesitate in terms of be very near to the threshold, but to increase the capacity of the femtocells. Meanwhile, the SARSA will try to be very careful with the actions it takes. So, as conclusion, we continue with the Q-learning algorithm because we will have better performance since the beginning of the learning process, and because we will guarantee the capacity at the macro user we want to have, but we will increase the capacity at the femto systems, and this will give us a higher global capacity.
Maria,
Okay,
sorry,
yes.
it's me again. And which is the cost of iteration, learning iteration?
In terms of what?
Of performance of the system. I mean, what is the meaning of how good it is? I mean, in terms of delay. I mean, in the previous slide, you say that one's is faster than the other one.
Yes.
Okay, but which is the impact in the system?
And that is why we decide to continue with Q-learning, because the impact will be that for a long period here we will be yes, the dash one, we will have higher probability to jeopardize the macrocell performance. So we are measuring this in terms of total transmission power. We don't want the femtocell to transmit higher than a given value, and this is the.
But my question is, have you measured which is the impact in joules of this improvement
No.
on the system?
No.
Okay, thank you.
You asked about the delay as well. I mean, if you put it in, if you put that in perspective, I mean, the 1 to the power 1 multiplied by 10 power 5, if you assume you have like 10 to 100 milliseconds feedback times, which is one iteration you can do, because you always need the feedback from the environment and stuff like this. It boils down to 2 hours, 2.5 hours. So 1 10 to the power 5 in LTE would be about 2 hours. All right, so just you get the idea.
No, but here we consider that the system start behaving well just after we start having a constant behavior.
Okay, so it's after 1 hour. Well, I mean, everything is, you know, you have to put it in perspective, because in fact you learn to live also in conditions, you know, which maybe don't obey your deterministic algorithms, meaning you learn and that's it. And then will operate for a long time well. So I think 1 hour is something we can tolerate.
Yes, right now I did the study, but now I can't tell you exactly. But yes, we arrived to the conclusion that we can handle this system, and also take into account that now here in these plots we are considering that suddenly a lot of femtocells start performing. So that is why we have so bad performance. But then we will have some femtocells performing, then comes one, and then comes another one. So this will be not that bad. Yes? Okay, so Quinn.
What is the probability of failure which is considered kind of good in systems? Because already the plot kind of starts from 15% failure.
Yes, but here you have to consider that we start with we consider one of the worst scenarios. So femtocells start transmitting very high power levels in order to guarantee or to show better the behavior of the learning algorithm. So we are taking very extreme considerations here.
No, then it's actually impressive, because the probability out of threshold is like 15% even at harsh conditions. So that's what my question is: if you kind of zoom that region in which your learning iterations start, and if your system can handle say 10% of probability, I'm not sure what the numbers are in LTE, then you might actually be able to do much faster. Because your probability, so the scale is like from 0 to 15%.
Ah, yes.
Yes.
Here
So
the
that's what I
maximum.
mean. Maybe.
Okay, so now we go to the the parameters we can tune in order to design a learning algorithm. The first one, and one of the most important one, is the learning rate, which will determine the importance we give to the newly acquired information. And we can, there are several forms to tune this parameter. You can use fixed values. Also, you can use linear values changing with the time. And also, you can use state action dependent values, which this means that the learning rate will decrease every time that you visit an action and a state and action pair. The other characteristic is the discount factor, and this determines the importance you give to the future rewards. As we see, the reinforcement learning algorithms aim to decrease this, to maximize the future rewards, or to minimize the cost. So these two these two parameters will give us, or will determine how fast and how good the learning algorithm learns. So in these plots, we represent the CDF of the probability to be out of the threshold in the whole learning period for the power and for the capacity. And here this is quite complex to see. We will see it in the next plot. But here the idea I want to show you, I want to transmit, is that the best combination is alpha 0.9 and gamma 0.9, because they give us the low probability to be out of threshold in the whole learning process. And now here in the time, we can see that if we fix the discount factor and modify the learning rate, if we have low learning rate, these two curves, no, this one and this one, sorry, the learning process will be slow. So because the agent will not give enough importance to the new acquired information, and the process will be slow. And on the other hand, if we have very high learning rates, the learning process will be kind of a mess. So the agent will do very strange things, because at the beginning it will give too much importance to the new information, and it will introduce noise in the knowledge representation. And on the other hand, if we fix the learning rate and vary the discount factor, we can see that if this discount factor is low, the learning process will be slower, because we are not taking enough into account the future in the learning process. So here there is a lot of work to do. I just have tried with fixed values, as we saw previously. There are 7.
So I think it's just because of my negligence of standards, but since we are taking like as Misha said, this process is going to take like 2 hours, right? But the gains we are getting are probably from like 6% to 2% of the probability. So is it really from say a operator perspective, maybe spending so much time on going from 6% to 2%? Because your y-axis is like, especially in the first plot.
This one?
Yes. So you're starting from 6% probability, and then you're going to 2%.
Yes.
But after spending 2 hours. So are these gains really worth?
Well, I would say yes. No, otherwise I'm working on that. But yes, because
there was a really good comment in the beginning, because we don't know how far we are from optimal, and so this infinitesimal small gain, is it really going to hit from overall system perspective?
Okay. From my point of view, this is very important, because each time that the agent is out of the threshold, this means that the macro use is not achieved the required capacity. This means that maybe it is around the threshold, you ask for 1.4, but maybe you are in 1.3, you are out of capacity. But this is good still. But maybe you are not receiving anything. So it's important because we need to guarantee. This is one of the key points in the Femtocell or the self-organization in Femtocell system, is that we need to guarantee the performance in the macro users. And this is our main goal. So from my point of view, yes, it is important to decrease this probability as much as we can, because this is what we need to tell to the operators. We are able to guarantee that the macro system will perform well, even though we are going to deploy a lot of Femtocell systems.
No, I agree. So the only point was that, I mean, suppose you're going from, say, as you said, 1.3 to 1.4. That can even be done by, say, tweaking coding modulation instead of spending 2 hours. That was just the point.
Yes. No. Well, continue. So now we arrive to the mentioned action section policy we have to follow in order to select the actions. And a very important characteristic of reinforcement learning algorithms is that we need to incorporate, we need to balance the exploration and the exploitation in the system. And this means that we need to exploit the acquired knowledge, but we also need to incorporate some exploration method in order to guarantee that the solution we are going to find is not a suboptimal solution, it's the optimal one for each state. Okay, so how can we do this? There are two main forms to do it. One is called e-greedy, and this means that we will select the best, we will select actions in a random way given by the epsilon value, and the other time we will do the rest of the time we will do exploitation, and this means that we will select the best action for the given state. And the other one is softmax algorithms or methods, which will select the actions based on probabilities. I will explain you this in the plot. Okay, so here we have 3 e-greedy algorithms and 1 softmax algorithm. This one is based on Boltzmann equation. And okay, so the first one and the most common one is the constant greedy. You just fix a probability to visit random states and you continue with this. We stop using greedy algorithm in here, so there are not going in here, so there are not going to be any random selection process, and we can see that the probability highly decreased from now on, from that point. So then we try to improve this method because it's quite simple, and we introduce a probability to visit the random state varying with the time, which is the black plot. And as we can see, at the beginning it doesn't perform very well, but with the afterwards it really behaves really good. So this can give a good form. This is one of a solution we are proposing. And the second one, which is also very simple, is to introduce 2 steps in the greedy selection procedure. So we start with a high value or high probability of visiting random states. For this plot, we start with 6%, and then we decrease it to the half, to 3% in this point. And as we can see, it decreases and continue decreasing after we stop using random probability. So one of the drawbacks of these solutions is that you will have the same probability to choose the worst action than to choose one of the best actions in that state, and that is where softmax solutions arise, because they will give a probability to select the actions based on the Q values you have per each action. And as you can see, it starts working very well, but after a period of time, it becomes completely greedy, so it will not explore anymore. And the problem here is that the design of this kind of methods is really tricky. It depends on the Q values, and what I mean with this is how you initialize the Q values, how they change in the time, so the cost function, how it's related the Q values with the cost function, and so on and so forth. So for me, from my point of view, the greedy action selection policy is a very good solution, because you will guarantee to visit all the actions, so you will know, at the end you will not only which is the best action, but also which is the worst action. So you guarantee that the agent will never go there. And finally, this is not very common to see it, the Q-table initialization, and this is one of the one of the solutions we give in order to solve some of these low convergence of the learning algorithms. And it's because since we know what the set of environments are representing, and also what the actions are, we can just do some smart initialization in the Q-table initialization procedure, and this will bring very interesting improvements in terms of the speed of convergence. So I will explain you here in the plot. As we can see, we can decrease again the probability to be out of threshold very fast if we include this smart initialization, which what we did was to just, for those states corresponding to powers above the threshold, we just initialize the Q-table for the actions with corresponding to transmission to low power values to a little bit lower Q initial values. So with this, we guarantee that if it's in a dangerous state or a bad state, at the beginning it will go in the best actions it can take, that is to decrease the transmission power. And this is what we gain with this, is to decrease not only the convergence at the beginning of the learning process. Okay, this figure is just to show you how the femtocell capacity behaves when we have different density of femtocells in the system. As you can see, if we have low amount of femtocells in the system, they will achieve high capacity levels. And then if we increase the amount of femtocells in the system, this capacity is not so high, because of course the intercell interference between femto to femto, and that's so the interesting idea here is that they are able to react also to the interference they generate to one to each other. So, as we saw, the implementation limits are the slow convergence behaviors. And also, one of the very important shortcoming of this kind of system is that they are based on discrete state and action representation. This decrease the accuracy of the system. So if we don't have, we have to choose between two power levels, and maybe the best solution will be a value between them. So this is a problem, and we saw it based on some simulation, that if we reduce the amount of available actions, the agent will also behave worse. So you can say, well, the solution is just to increase the amount of actions and the amount of states to represent the environment, and that is true. If we increase the amount of state and action values, we will have better performance. But this is not scalable, because we need to store a Q value per each state action pair, and this needs a high memory requirements, and therefore we cannot scale these to big scenarios. So also, well, this was just what I say. The search space will increase, so we will need more time for learning, and also the complexity of the system will increase. So to solve this solution, to solve these problems, I just have to go very fast now. We propose two solutions. Docition, which is a cooperative technique, which will be based in the learner-teacher paradigm. This is in order to solve the problems of speed of convergence, and the other one is to combine the fuzzy logic with the Q-learning algorithm, and this will allows us to have continuous state and action representation. So, okay. Since we cannot go much into details, I just want you to have the ideas of these solutions. And docition, the word docition or docitive comes from the Latin word docere, which means to teach. And the idea here is, since we will have femtocell systems in our case that have been learning for a long period, and then I arrive and I don't know nothing about the environment, I can tell Misha, can you teach me something I can use for my starting? So we can share this knowledge, or he can share his knowledge with me, and I will behave much better since the beginning of my operation process. So the idea is that we will save. We will have important savings in the learning, in the required learning time, and this can translate in energy savings, of course, and also that we will have much accurate behavior since the beginning of the learning process. So the idea here will be we will have this box. In this box we will have the learning procedure common. We take intelligent decisions based on the state of the environment we are perceiving, and we take actions, and so on and so forth. But here we have the new component in the agent, which will take into account how to compare agents, how to know how good is my behavior right now, and how can I relate my performance with other agencies in the system, and what I'm going to share or to teach. So these are the main characteristics: from whom to learn or to whom to teach, what to learn and when to learn. So to select from whom to learn, we have to guarantee that those agents have the same impact in the system or in the network. We can learn everything. This is the case, for example, when a new agent joins the network, or for example, if I realize that I'm behaving really bad, so I need to start over. Instead of start learning again since the beginning, I can just erase my Q table and copy from another more expert one. Or maybe if I can't interchange so much information, because maybe I need a long time to get all the information, I just can copy part of the knowledge. Maybe those information to the critical states, for example. And when to learn, this is really related with what I was explaining before, because I can learn just at the beginning of the learning process, or maybe I can do some periodical learning information exchange or docitive exchange. So we propose two solutions: the startup docition and the IQ-driven docition. The startup is just for copying or to learning from docitive radios at the start of the learning process, and the other one is to learn during the whole learning period. So let's go to the results. As we can see, we will have much better performances when we use the Docitive techniques in terms of outtouch probability, and in terms of capacity, we will guarantee the same performance as for the independent learning. Yes.
We're looking at the solid curve with the circles. So startup,
yes,
Docitive.
So the x-axis.
Okay, it starts at 0.01.
Yeah.
Okay. And then it decreases, but then increases and then decreases again.
Yes, but this is common. Okay, this in stable behavior at the beginning. Sorry, there is a mistake in the x-axis. I didn't realize it. Sorry about that. But this unstable behavior here is because the agents will be not the same. So I can learn from someone which is behaving better than me, but our situations are not going to be the same, never. So what I will have when I learn from other one is that how to behave in how to start my learning process. But of course, after the learning process or the Docitive process, I have to adjust this knowledge to my situation. So this is just to give a starting point better than my own. Okay, and then if we do this, the IQ driving decision, the idea here is that it's very useful when you can have noisy information, maybe because you have your sensor is not performing well, or you have noisy information, yes, and that's all. So you can guarantee that at least for the critical situations, you can always behave well. You know, so this is the idea, to take advantage of this knowledge that the system already has and to share it. Yes? Does it answer your question?
But we can discuss it later.
Okay. So, okay, so I think we don't have much time, so I just want you to have the idea about the Fuzzy learning. Since for the state representation we need to use some thresholds here. So in our case, what we did was to know if the total transmission power was above or below the threshold, and the same for the capacity, it was above or below the threshold, but we don't know how far we are. And for the capacity of the femtocells, we just set some threshold also. We will have a very inaccurate state representation. And the same for the actions. We can have, for our case, we use 60 power levels, which is a lot, and that is why we also have so long learning period. But if we could translate this, or to represent this somehow in continuous form, we will have for sure better performance, because we will know the real state, and we are going to be able to take the real or the more accurate action for the given state. So we have 3 steps. We need to do a fusification process, compute some true values, and then to fussify these true values. And with this, we will have continuous. We will represent continuously the inputs and the outputs. So I will not go into details of this. I just want you to see that when we apply this Fuzzy learning, we are going to be able to have better performance for the macrocell systems, and this is just because of what I was explaining. We will be able to take more accurate actions per each state, and this will translate in performance. And now we see the convergence behavior. with this, we will have also, this is for 60% of occupation ratio, and the previous plots, sorry, were for 45. So the idea is that with this we will decrease the probability to be out of threshold, because when we design the fascicule learning, we will introduce some knowledge, because we have to include some rules that the agents will have to follow, and this decrease the probability or increase the convergence behavior. Okay, so finally, since as Misha mentioned before, we will need to know some information about the macrocell system performance, and to do this, we propose to the macro base station to send a downlink high interference indicator. We assume that there will be an X2 interface. Since this is not still standardized, we are working on some solutions to solve this problem. And this downlink high interference indicator will be equivalent to the one that Subin explained us yesterday, which is the relative narrowband transmit power. This indicator tells us with 1 bit per resource block where do we have high interference or low capacity. Or I mean, we can use this idea to design our indicator. And of course, the threshold is the threshold and the time period for the indicator are configurable parameters. You can find more information in this paper. And that's all. So with this, I conclude my talk. We have said that self-organization is required, or is a very good solution to solve some problems in next generation wireless systems. We propose to apply some reinforcement learning techniques. We have seen important characteristics of this kind of learning algorithms. We have studied how to design them, and finally, we have seen some improvements for the learning algorithms based on cooperative and fuzzy logic, cooperative techniques and fuzzy logic. So that's all. Thank you very much.
Excellent. Thank you very much. Any further questions? I think we had a pretty good discussion. As Evgeny has one.
Well, at the end of the day, you got some kind of database of Q values, yeah? Have you tried to use it to derive some kind of universal strategy for all the femtocells, or some kind of analyze the whole Q values of the system by agent to agent?
No, I haven't tried.
Well, probably, do they really differ between femtocells, so these Q tables?
Pardon me?
Do they really differ between femtocells? Probably you can just fix this strategy and use it for all femtocells, and you get it without any convergent problems, no?
I don't know if I get your question, but since the representation of the environment will be the same for all the femtocells in the systems.
Well, these Q values, are they really differ between agents?
Yes, of course, it depends of the experience each agent will have in each iteration, and you cannot, you will never find the same Q value between two different agents.
Okay, thanks.
No, because it depends of the experience of each, in each moment of each agent, and the situations you find.
Particularly the experience. I mean, you may have a femtocell which is close to window, one really deep in the room, so I think their Q values will be very different. Yeah. Exactly. Which posed also one of the problems in the decision, because it was difficult to decide with whom change the intelligence waves. In the end, we decided to use just an Q value exchange between femtos which were in similar operating conditions.
Exactly.
Yeah.
In the decision example I showed, we try to measure this relation in terms of the impact the agent was having in the state of the environment, and that's well, a form to compare.
Okay, there are no further questions. Thank you very much.
Thank you. Before, I would kindly invite you to consider to submit to the second international workshop on cooperative heterogeneous networks, which will be held in Munich as in conjunction with the ICCCN conference. It will be the 30th of July.
Good summertime. It's worth coming to Munich at that time. All right. Now we need to rush to lunch because we are competing with a much larger group, actually. There's a cost meeting just beside, so we don't want to queue so long. So let's rush just off. And we're also having the social with them, by the way, tonight. So we're going to be a larger group.